Greetings and welcome to the Dr. J Vlog series. It is Thursday, June 5th, 2025, and on Thursdays we talk about knowledge and science. Baryonic matter refers to ordinary matter. It's the stuff that we see in everyday life, although such matter ultimately breaks down into much smaller entities such as molecules and atoms that of course we don't see directly per se, and even subatomic matter. So what's truly incredible, though, is that the baryonic matter, that's, again, the stuff that we're aware of, that we see all around us, comprises only about 4.5 to 5% of the total mass energy in the universe. So what's the rest? Well, it's believed to be a combination of dark energy and dark matter. In one paper I was reading a few years back, the author, Chung-Ding Yu, calculated that the theoretical percentages of dark energy, dark matter, and baryonic matter are about 72%, 23%, and 5%, respectively. And other calculations and more recent calculations differ somewhat, but it's hard for me to wrap my head around the idea that 95% of the universe, at least hypothetically, consists of dark energy and dark matter. The reason, of course, is that the reason that's so incredible is that we haven't been able to observe this stuff, at least not directly. We've not been able to observe dark matter, for example, because it doesn't interact with, apparently, with baryonic matter. And it's completely invisible to light and electromagnetic radiation. So, how do we know it exists then? Well, we can only infer its existence based on its gravitational effects. That is to say, the effects that such matter appears to have on galaxies and galaxy clusters, for example. So according to the standard physics approach, stars at the edges of any spiral galaxy should travel much slower than those near the galactic center, where a galaxy's visible matter is concentrated. However, the evidence reveals that stars orbit at more or less the same rates, same speeds, regardless of where they are in that galactic disk. And so this only makes sense if one assumes that the boundary stars are somehow feeling the gravitational effects of some kind of unseen mass like dark matter. So, dark matter could also explain certain optical illusions that astronomers see in deep space. And that's, again, it's an incredible set of anomalies, and yet the problem is that we aren't able to make sense out of this unless we assume the existence of dark matter. So, but again, we don't have any current means of being able to verify what might be happening or what exactly dark matter might actually be. So the main hypothesis is that dark matter consists of these kind of exotic particles that just don't interact with normal matter and light, and yet still exert this gravitational pull. And so several scientific groups, including one at CERN's Large Hadron Collider, Switzerland, are currently working to generate dark matter particles for study in the lab. So I await to see what happens in that front. But if you think that's strange, dark energy is even more mysterious. In fact, I took an astronomy class in university back in 1984, and there was absolutely no mention of dark energy. Now, why not? Well, because it wasn't discovered until the 1990s. Before that time, physicists assumed that the attractive force of gravity would slow down the expansion of the universe over time. In fact, some hypothesized that eventually all of this attractive force would eventually reverse the expansion of the universe, and eventually that the universe would start to collapse back in on itself. So the idea is that we'd go from a big bang to a big crunch. I actually remember reading a book by Isaac Asimov on the ways that the world or the universe might end. And that was one of the theses that was discussed. Again, this was back in the 1980s, though. But anyway, this turned out to be almost certainly wrong. Well, how so? Well, because independent teams tried to measure the rate of deceleration, and guess what happened? Or guess what they discovered? They found that the expansion of the universe was actually speeding up. I can only imagine how shocked they must have been with that discovery. Most of us, of course, will never be on the front lines to make these types of shocking discoveries, but it's still, at least speaking for myself, it's still why I really enjoy learning. I love being blown away by learning these truly new things that just amaze me. And those most incredible scientific and historical or even artistic discoveries and inventions will always, for me, be a source of wonder and amazement and inspiration. In any event, scientists believe that the accelerated expansion of the universe is driven by a kind of repulsive force generated by quantum fluctuations and otherwise so-called empty space. Empty space may not be so empty. The unseen force seems to be growing stronger as the universe expands, and this is what we refer to as the dark energy force. So at the present time, again, we don't know why it exists. Some scientists speculate that it might actually be a fifth fundamental force that sort of fills up or fills out or fills up the vacuum of space, like some kind of hidden fluid. It might be the dominant force in the universe, tying together the remaining cosmological mysteries and as yet that haven't been solved by astrophysicists. So, according to the most recent estimates, then, by the European Space Agency's Planck mission, dark energy is estimated to contribute about 68% of the matter energy density of the universe. So, less than the earlier figure that I cited. And so that 68% value is found by tuning the parameters in the famous concordance model of the universe until its output matches our current observations. So the possible properties then of dark energy are consistent with what we refer to as, and what Einstein referred to as a cosmological constant, a mathematical sort of band-aid Einstein invented or added to his theory of general relativity to make the equations fit with the notion of what was then believed to be a static universe. So according to Einstein, the constant would be a repulsive force that counteracts gravity, keeping the universe from, again, collapsing in on itself. He later he got rid of the idea because the facts revealed, or eventually, actually in 1929 with Hubble's discovery, that the universe was actually expanding. And so Einstein basically called this notion of a cosmological constant his biggest blunder. Well, not so fast, Einstein. Nowadays, we include dark energy in the concordance model as a cosmological constant, which describes an intrinsic property of the vacuum of space that is the same at any point in the universe. And so now that we see the expansion of the universe is actually accelerating, adding in dark energy as a cosmological constant could neatly explain how space-time is being stretched apart. Again, that idea, when I first heard it, just blew me away. Perhaps you as well. The only problem is that we still don't have a clue as to why this force exists in the first place. And so this leads to my final point today, at least in terms of physics. What is positive energy? Talking about positive energy all week. Well, it may sound incredible, but many scientists believe that the total energy of the universe is zero. Hence, no energy needed to be created even when the universe came into existence. While it seems obvious that there's a huge amount of energy in the particles and the radiations and so forth that pervades the universe, this energy may be balanced by negative energy caused by the gravitational attraction between particles. As Stephen Hawking once explained, when you pull two objects apart, you need to expend energy to overcome the gravity that holds them together, pulls them together. And so it takes positive energy then to separate them. And if that's the case, then gravity must be a form of negative energy. Certainly a form of negative energy when I go up on the hoop and try to dunk, but I don't want to get negative here. But my vertical is definitely much more of a horizontal these days. But anyway, but if that theory is correct, then there was never any need to create energy or matter. They cancel each other out. And that implies then that the Big Bang could have started as a result of a simple statistical fluctuation. Of course, we don't know. Right? We know pretty well what happens right back to the earliest instances in the universe, but we don't know what happened at that first moment. Again, it's theorized, this Big Bang notion. But then where would that have come from? And so on. So the zero energy universe hypothesis is the simplest explanation, as outlined just over a half century ago, back in 1973 by Edward Tryon, who was the first to suggest that our universe is the result of quantum fluctuation. So we already know from the first law of thermodynamics, right, that energy can neither be created nor destroyed. And in a way, that's highly consistent with the zero energy universe hypothesis, which proposes that, again, the total amount of energy in the universe is exactly zero. So in other words, the total amount of positive energy in the form of matter is exactly canceled out by the negative energy in the form of gravity. And so to me, this is the great mystery then that has to be solved in the 21st century, at least in terms of physics and cosmology. The standard model of particle physics does a remarkable job of identifying the necessary parameters and the values that explain three of the four fundamental forces, electromagnetism and the strong and weak nuclear forces. But it doesn't incorporate the full theory of gravitation as explained by general relativity. And Einstein and many others have since been searching for a unified theory that does everything that the standard model currently can do, plus explain gravity. And I think implicit in today's brief log is the reason why that might not be possible, at least as currently formulated. There's no consideration or proper modeling of both the dark matter particles and no final solution that involves the dark energy that appears to be driving the universe's accelerating expansion. So basically, the standard model doesn't include a particle that could explain the observed gravitational effects of dark matter, such as the rotation curves of galaxies and the fact that galaxies come together in clusters. And so the idea of dark matter is composed of the idea that it's composed of these new fundamental particles beyond the standard model and their interactions. All of this could be then related to gravity, or would need to be, in my view. And similarly, the presence of dark energy hasn't been incorporated into the standard model either, which doesn't explain, again, the expanding universe. And thus, the presence of dark energy would almost certainly require some modifications that could accommodate a new understanding of gravity. And so there are, of course, a number of people who are working on the problem. And as I've briefly discussed, I think the resolution then has to involve some way then of reconciling what many these days refer to as quantum gravity with the alleged and overwhelming presence of dark matter and dark energy. So, and I'm confident that a big breakthrough along these lines will actually come sooner rather than later, or in fact, sometime in the current century. I don't know when, of course. I just hope that I'm around for that particular jaw-dropping discovery. So to me, that would be one of the greatest discoveries that could change our entire view of the universe. And actually, that to me would be only second to something I talked about in an earlier vlog. That is the discovery and verification of life elsewhere in the universe and how that came into being. So anyway, that strikes me in general as an interesting vlog to do. Maybe the top 10 list for the greatest future discoveries or resolutions to the greatest mysteries in the known universe. Okay. In the meantime, and as always, may you and yours continue to create peace in your lives, nurture love in your hearts, and dole out hugs in abundance. And I hope to see you soon, maybe even tomorrow. Take care.